3 microliters. So what? Yeah, yeah. They're big, it's sort of the same amount of, yeah, they're big samples, but we still sit, so we probably don't even have to sit on them for as long as we do. And that's what we're trying. So right now at Michigan, we're trying to, the lab's almost ready, but we're trying to automate this, and we're trying to just streamline it so we can pump out more data. Yeah. Brian?
Did you say that was in good comparison with
with an LGR instrument. And both of them are making the measurement.
Precision is necessary to make reasonable interpretation?
Technically, yes, but there's no practicing lab that's making the LGR measurements. This was done in the factory, at the LGR factory by the technician to make it, and that's the study that came out. Eric Steig's lab at Andy Schauer, who used to work here. So Eric Steig's lab is working using the Picaro, and they're making. So the Picaro and the LGR do use slightly different sort of techniques to make this measurement. They're using the Picaro routinely, and I think the Picaro and they're using it also with ice. And I think that in some ways, the LGR and the Picaro do different. They sort of get around these problems in different ways. The Picaro basically just has like very stable sort of measurements and doesn't run very many standards, but sort of measures things for a long time. I think the fact that Eric Steig's group is measuring ice, they're running very consistent kind of samples, and they basically, so I think that helps them. I think for running a variety of grab bag samples that we run, I'm not sure how that translates. So it's getting there. This Schoenemann paper, this is one of Eric's students. That lab, the thing about that lab is that they have fluorination and Picaro up and running, so they can calibrate what they're doing. So they're actively calibrating their Picaro work to their fluorination work, so they have that sort of crosstalk. It's not there yet. If someone's about to spend their startup money on one of these, talk to me first. Don't do it unless you really have a very clear plan, because it's not there. It's not as there as they think, as they're selling it as it's being there. However, people they're taking water out of gypsum and measuring on the Picaro for sort of fluid inclusion. So it's getting there. It's close, but it's not there yet. This issue, what's something that's interesting with these Picaros, we have the benefit of, they use different lasers for the 18O measurement and the 17O measurement, which means their errors aren't correlated, which means they don't actually have the benefit of this, okay? So they need their precision of their little delta values just as good as their precision of their CAP 17O, because their errors aren't correlated. That 17O and 18O, I measured on the exact same molecule, right? That goes into the same bellows, it sees everything, right? So those errors, but that's one of the challenges of their system, that they're not correlated. So I've sort of been involved in this, and I want as much as possible more people to make these measurements, because there's so much to be done. And the Picaro and LGR, they're so enticing, but it's not totally there yet. And the calibration of these measurements is slightly different than the calibration of just regular delta 18 and delta D. So there's a little bit of a mind shift that has to happen. So where we are in terms of analytical advances, so some people have been measuring carbonates in various different ways, but maybe I'm biased, but Ben in our lab has the most tractable method for measuring carbonates, and it's part because we can measure it in water. So basically he digests the carbonate to CO2, then we reduce the CO2 to water, which seems crazy, but it's not crazy if you know that you can measure that water really precisely through our fluorination method. So that's one method. For CO2, people have been equilibrating water with CO2 and then fluorinating that water. You sort of really need to know your water, your composition of your water very well. So you need to know, this is technically possible, but there's challenges associated with it. Silicates and oxides are very tractable. People have been doing this. This is a huge growth field. Bioapatite and phosphate, Gaylor et al. Have been working on this. This is out of Andreas Pock's group in Germany. There's other materials too, and I just put this here. It should be possible in cellulose. It should be possible in lots of different kinds of materials. Cellulose to me is really exciting, because just as you think about this water talk, if we could get this in tree rings, this could be really powerful and very exciting. So there's lots of different kinds of materials that preserve oxygen, and it's an analytical hurdle to just, we now have all the pieces, and now it's somebody who just needs to focus on sort of doing it. And so all these things are, if you need to have your eye on the prize, you need a big slam dunk kind of, you need a reason to do it, but this is a huge growth field. So So why am I doing this and why am I spending all this time? So thinking about this, let's get to the processes. So let's just think in delta H and delta D space, again, in terms of kinetic fractionation. If you do an open pan experiment, so you have water and you start just letting the water evaporate. And so this is an experiment that Shu-Ning and I did, and then we just sort of collected. We had a bunch of pans out, petri dishes of water, and we just sort of collected them at certain intervals of time. The delta H of that water increases, right? That makes sense, through evaporation, right? That d excess of that water, sorry, I'm standing here, right? That will decrease. So like as you go, your kinetic fractionation, your d excess, as you're moving along this kinetic fractionation slope, your d excess is going to become more and more negative, and that's what we see in d excess. The same thing happens in 17O excess, okay? And so I'm just going to do this little, PowerPoint, little trickaroo. So the same system, delta 18O, 17O, the kinetic fractionation line is a lower slope. The same thing happens, the delta 18O didn't change. As delta 18O increases, cap 17O decreases because you're coming off of that slope, okay? This is the power of this. So if you can basically, to me, there's lots of different things that you can record, but in terms of getting a metric of evaporation, and that this change in delta 18O is due to evaporation, and a way to sort of diagnose it as a function of evaporation is through cap 17O. And these are big cap 17O sort of signals. So now we're getting to 0.3 per mil, that kind of range. Okay. I can't, because the differences in these kinetic, I erased it, but between the differences in slopes are so small, I can't visually see it. I can't see the difference between a kinetic and equilibrium fractionation. If I plotted all these data on a slope like that, they would just all look on one graphic. So what I'm going to do is I'm going to show you all the delta 18O data, the 17O data on a space of delta 18O on the x-axis and cap 17O on the y-axis. So anything that's following my reference slope, or what I'm defining here as equilibrium, so I'm defining it for you. And I'm defining my slope as 0.528, and that's basically what our meteoric waterline slope is. So I'm always defining it here. So if anything falls on the slope of 0.528, which is pretty close to equilibrium, it should have a flat line effect. So all the change in delta 18O that's happening should see no change in cap 17O, right? There's no residual, so the residual is constant. If, however, kinetic processes, and in this case, let's say evaporation is driving it, then you should see an inverse relationship between delta 18O should be increasing and cap 17O should be decreasing. So I'm going to show you guys all the plots in this space because there's going to be no interesting information in that space. So in this space, we see that's, with those same evaporated samples, as you evaporate your water, they're increasing in delta 18O, they're decreasing in cap 17O because you're deviating from that line. If there was no evaporation, they would just fall in this straight line. And as you would expect, if evaporation is driving it, we should see a really nice linear relationship between d excess and 17O excess, or cap 17O, and we do. This was just a sort of a very simple Craig Gordon model that we modeled, so that they're it's off from our model approach, and we could go into, what parameters we sort of got wrong. But in this case, this evaporation, for every 1 per mil change in d excess, we see a 2.2 per meg change in cap 17O, okay? And it's a linear relationship, and we keep seeing that. So that's pretty exciting to me, that when evaporation or kinetic processes are driving the fractionation, we see a very systematic relationship between d excess and 17O excess, and we'll continue to see that. And we've seen that in plant waters, which is really nice to see. Okay. The other sort of funky thing that I just want to plant a seed in this, just to give you an idea of it, is that delta in this space, in cap 17O space, remember, it's not linear, right? We've done this log transformation to those delta values, okay? So if I mix things in cap 17O space, mixing is not linear, okay? So if I mix some of that evaporated water, some of that, let's say, I don't know, plus 20 per mil water with water from Vostok, which is like, negative 35, negative 40 per mil, delta 18O is linear, right? That's actually, we should totally expect it. But when you take a mixture of this cap 17O values, and you can do this quickly, we could work it up in a quick Excel. You can put funny numbers, your own numbers in, and you can do it. You can mix delta values. The mixture, and this was this evaporated water, it was low in cap 17O, and the Vostok water is sort of normal meteoric water, cap 17O. But the mixture between them is not a linear mixture. The mixture in cap 17O and any sort of triple isotope system, you see this in sulfur isotopes itself, it's a function of these delta prime notation, and it's more negative than you would actually expect. So it's another way, it's a function of the math, basically. But it's another way to kind of mixing actually has an isotope effect in some sort of way, in the way that we're presenting these isotopes, okay? If you have mix things that are close together in little delta space, there's not going to be a big effect. But if you mix things that are far apart in little delta isotope space, you could have a big effect. That's cool, right? You can start to see that how this could possibly be useful. Okay, so let's just sort of stretch. I know I'm throwing, like if 17O tracks evaporation, instances of kinetic fractionations, what applications could you envision? What would you tackle? What would you want to analyze? What would you want to know before you started these kinds of investigations? So is this sort of starting to, is anyone getting ideas about this? Oh, sorry, as I shoot a laser in your eye. This is like the part of the talk where I was like, okay, I'm going to insert something interactive so you guys, it breaks it up a little bit. So maybe, okay, how about everybody just stand up, stand up. Yeah.
Fluid inclusions?
Yeah. So fluid inclusions in what?
Evaporates?
Evaporates to learn what? No, you can end there. Fluid inclusions are an awesome way because actually we want to understand fluid inclusions are these crazy things where in rocks water gets preserved. Like old rocks, old water. That's very cool. And it's been measured for delta 18O and delta D, but it would also be really cool to measure 17O to have just another constraint on what's driving that variation and there are different pools of water deep down in the earth and what if we can understand the exchange of them. And then also we can then measure 17O in the included inclusions and then maybe also in a pairing mineral to try to understand it. So yeah, I think fluid inclusions would be I would give you some analyses. We could actually, and people have been doing it, and I actually think it's the challenge of that. We've already solved that problem because now we can measure the water, and other people have figured out how to measure delta 18O fluid inclusions well. So we just have to marry two different existing techniques, right? So it's not like we don't have to reinvent the wheel and everything, like just one thing, and then use anybody else while we're standing up. Yeah. TUFA. What would you want to know?
You could look at potentially like kinetic isotope effects in groundwater over time.
Yeah, and tufas in caves, so a lot of the speleothems, so there's been awesome paleoclimate records from speleothems and 18O, but a lot of problems with speleothems, which are cave carbonates, is that people don't know the influence of kinetic fractionation. We might be able to test this, right? Because we have something, it's not evaporation, but also kinetic processes are going to drive this, going to have that lower slope, okay? Anybody else before we sit down? Okay, we can talk later. It's okay, I'll let you guys sit down. But yeah, there's lots of things that could do. So I'm interested in carbonates. I'm interested in soil carbonates. I'm interested in fossil teeth. I don't have a hope and a prayer to do any of this stuff in the geologic record if I don't understand waters, okay? If I don't understand those inputs, if I can't come up with some sort of model of like, well, if I think I just need to understand waters. And so this is where I've started. And plus I knew that the measurement was easier. So I'm gonna, and I won't get through all of this, but I'm just gonna give you a taste of the work that we've been done in waters. So Boaz Luz's group at Hebrew University has been a pioneer in this and translating, the first one to measure waters. And he did the classic geochemistry thing, a geochemist approach of like, we can make this measurement. I can make this measurement now precisely in waters. He had a 2005 paper. I'm now just going to go out and measure a whole bunch of waters and see what I get, right? Which is like, it was new. And so he came up with a meteoric water line for waters. No one had ever done it before, right? This is all within that gray ellipse. It's all within the mess, okay? So this is delta 18O, so negative 60 to 0. And he found a variation in cap 17O between 0 and 80. Seawater is defined as 0. It's right here. And so he said, okay, the average meteoric water value for cap 17O is 35 per meg. That's like saying the average global meteoric, that's like the 10 per mil in d-axis, right? That's basically saying, he said, okay, it all works on a slope of, so instead of this slope being, so the equivalent, we have this slope, the equivalent for here, and I'm going to put prime notation on here, 0.528 times delta prime 18O is plus 0.035 per mil. All right, that's basically the equivalent relationship, okay? So, yeah, did you have a question about that? Or?
Is this a geographical or global?
Yeah, it's like the geochemist sampling. It's from everywhere. A little bit from Israel, a little bit from Europe.
But you only have like 4 samples of rain.
I know. That's a great point. But no one could make this measurement before. This is the first time we ever knew the distribution of waters. Everyone just thought it was 0. There's nothing to look for here. So
Do a local calibration in your area?
I paid you to ask me that question, be like, duh, like, why didn't they do this? It's basically because it's just like, this is a lot of work. It's a lot, no one's ever done it before. This is step one, but you're right, we'll get there. I did it. I answered your question, yeah.
Do we know anything about the 17:0 trends and precipitation through events or through season?
Yeah, okay, you guys. All right, I will pay you guys after the lecture, okay? You guys did a great job, okay? So I was not satisfied with this, right? It's like, there's no rain. This is like, come on, this is totally weighted by all these like snow and ice samples because you have a postdoc who wants to do this in snow and ice. Like, this is totally biased. Like, come on, we need more. I don't, okay, so more people sort of did this, and then things sort of started to get a little crazy. These snow and ice samples, like, people started to measure more of them, and they got really weird. Like, uh-oh, come on. This 35 per mil is starting. So this is a whole set of, so there's a group actively working on snow and ice for paleoclimate work. It's very exciting, cool stuff. This is actually just I won't go into this, but this deviation, they actually think that these are kinetic effects, right? They fall below the line. Kinetic effects during snow formation, really cold temperatures, right? These are really low delta 18O values, really cold temperatures during like super saturation of snow. So there's some kinetic process that happens cold that they're picking up with 17O. Pretty cool. Okay, yeah. Maybe. Yeah, if there's kinetic processes happening, we might be able to pick it up. Yeah, so this is like, we're in exploration mode. We have a good theoretical reason that there should be a continent called North America or maybe India, but we just haven't been there, right? So we just have to go there and make sure that our maps are right. Like, this is what we're sort of at this point now. We have sort of expectations from all the delta 18O and delta D work that we've done of what might happen. We know 17O works slightly differently, and now we're going to these places and we're starting to figure out what's happening. Okay, so this is where we are. So we have lots of expectations, and you want to basically choose your crews wisely, right? So if you want to keep on my explorer analogy. So people have analyzed more rain, and we're starting to see a lot of really more interesting variation here. So one of Ama El Landé, she runs a group in France. She ran these samples. She was that postdoc working with Boaz Luz, and she's now set her own lab up in France. She sampled 17O in a rainfall in Niger and came up with these really cool results. This is time in minutes after the start of the rain. And I forget, no, I might have actually messed up these units because I replotted. These actually might be minutes, but it doesn't sort of matter in time. But this is time in minutes after the rain. Relative humidity starts high and it tapers off. Precipitation rate starts high and it tapers off. Delta 18O starts high and it starts to taper off. D-axis starts high, starts to taper off. And cap 17O has a slightly different relationship than D-axis. And then what I did is I replotted her data. And I think this is, so the first part of the rainstorm is this blue. And there's no correlation between D-axis and 17O axis. And the second two phases of the rainstorm, they start to correlate.